you see a little bit of an effect when we take off residue. In fact, in both these systems, our yields in general have gone up. And that's usually related to the fact we get a little bit better germination. We don't have as much residue out there to handle. You get a little bit better germination. The corn gets off to a little earlier start, and that's why we get a little bit better. And it's been fairly consistent. The other thing you'll see is the no-till is less than the conventional or the disc tillage system, and that's been fairly consistent. This is a corn system, and that system, if you make just a pure switch into no-till, that has been a problem. It takes a while for that system to get to the point where your yields are going to be pretty much similar to they would be in a tilled situation. If you're in a corn-soybean rotation, it doesn't seem like it takes you quite as long, but for some reason, in a corn system, it takes you a while longer to get those yields up. The no-till will eventually, and it seems like it's worse in an environment, or no, I shouldn't say worse, but it takes it longer in an environment like this where we've got more water potential. As you move to the drier areas like to the west, the no-till, the yields come together a lot quicker. The only other thing I want to point out is to give you some idea of potential production. Let's say if you want to, taking this residue off, right now we're taking at the 50% in the system approximately 2 tons. And to give you an idea, that's about 79 gallons per ton of ethanol would be produced. So right there we'd have about 160 gallons of ethanol. This is a no-till corn system. We're comparing it to switchgrass. And our initial objective for the study was to look at, we figured on these, we were going to demonstrate on some of these marginal soils that this is why you put something like a perennial crop such as switchgrass or something like that on that type of site, because it's there year-round. You reduce your erosion potential and everything else. You don't have to replant it every year, and we figured, well, by golly, it's going to outperform any row crop situation we've got. Well, in this environment, we get enough precip that actually our no-till corn has not done that bad. It's when we look at it, I mean, the yields aren't extreme. Don't get me wrong, but what I'm talking about, when we compare this system to the switchgrass system from an ethanol standpoint, we're actually about tied. We measured organic matter levels before the experiment went in, which happened to be 1998, and then we came back in 2007, which was after 10 years. And what I've got here, it's in metric units, just ignore that, but because this is looking at the change in soil carbon we've had over that 10-year period. And this is 0 and all the numbers above are positive. And then across the bottom, of course, we've got the different nitrogen fertilizer rates, which are here. And then what I've got here is 0 to 30 centimeters, which is just the top foot, or 0 to 120, which is the top 4 feet, or 0 to 150, which is the top 5 feet. What was really surprising to us, especially in this lower production system, is we had got a lot more carbon that we put in the soil. We got a lot more in the surface foot, but what really surprised us was we got a lot more at depth. So we're putting carbon down at depth. And the good thing about putting carbon down at depth is it's a lot less likely you're going to lose it if you come back there and till that soil.
The reason why we're looking at cellulosic materials, again, is that the thought is that originally it's fairly abundant. The cost is at the point where we think it could be comparable to petroleum at high petroleum prices. And one of the things is that back in 2007 there was a law that was enacted called Renewable Fuel Standards, where they basically said that this year we're going to have corn ethanol capped at this level, and then eventually we're going to cap it at 15 billion gallons per year. And then at the same time, they also said we wanted to use cellulosic ethanol. We're going to cap it out about, in 2022, about around a little over 22 billion gallons of ethanol. That's just quite a bit. It'll be higher than corn grain ethanol. So what we're trying to determine is how much can we take off, and what is the total the energy efficiency of this system. We're looking at about a 1,200 pound bale or so. At a conversion rate of about 80 gallons per ton, that bale is equivalent to like a 55-gallon barrel of ethanol. So every time you see a round bale out there, that's equivalent of a 55-gallon barrel of ethanol. The amount of energy the fossil fuel energy that's required to produce that is about 5 or 6 gallons. So there's a fairly high energy balance there. And that's one of the things that a lot of people, when they first did the initial calculations and the thought process, is that this is a very sustainable system. And you want a high energy balance. I think probably some of you always have this in the paper or in the news about this corn grade methanol, whether it's lower or better or something, or have a high energy value and so forth. Most of the consensus is that it has a net energy balance, which is a positive, which is a good thing. But they also, most people note that the cellulosic part is going to be even higher. We already have, I think POET just got a loan from the Department of Energy for about $109 million about the last 2 weeks or so. There's already a facility, another facility in Iowa that's going to use the corn cobs for potential cellulosic ethanol. And the reason why they're starting to look at corn cobs is, one is that if you're taking that, again, there's too much stover off, you may be losing carbon, that's a concern. Secondly, the cobs are a little bit more dense. You can transport them. Transportation costs are fairly high. You can't use a large radius to collect this material and try to bring it into a centralized location. So the more dense material it is, the better off it is. And the third thing with the cobs is that it's easier for them to, it's more of a stable. There's not much fluctuation with the hemicellulose and cellulose, so it'll be easier for them to break down, and the plants will be more optimized over time.
The first study we did out in York County with a producer that we were working with. We had a full field that we were working on. In that field we had strips where we went through and we collected the stover. He used it in his feedlot operation. And then we also had strips where we didn't collect any residue. So we had residue retained, residue removed. And then within each of those strips we found parts of the field that had fairly steep slopes, 10-11%. And we went in and we put in some runoff plots, and we collected cobs out of one plot and left the cobs in. So what we were trying to do is just see if the cobs had some role in soil and water conservation. Because they're dense, they've got a fairly small, they cover a fairly small area of the field. So our hypothesis is that they really didn't have a real big role in protecting the soil from erosion, and that's in fact what we found. The second study we did, we went out and picked up a bunch of cobs following harvest a couple falls ago, and then we followed the decomposition of those cobs during this following growing season to see what happened in terms of the nutrients contained in the cobs and then also the carbon. And we used some of the same no-till sites that Gary was talking about. We had an irrigated site and a rain-fed site. As Gary mentioned, the production levels at the irrigated site are higher, so you start out with more dry matter at the beginning of the study than you do in the rain-fed system. We took some of the cobs and we buried them in the soil to simulate either tillage or getting them pinched in during planting or fertilizing or other field activities. And then we had the rest of them on the surface. And when you bury the cobs in the soil, they're in more intimate contact, they're more available to the soil microbes, they stay in a moist setting longer, so that decomposition occurs more quickly with those cobs than the ones that are placed on the surface. And also the other thing, in the irrigated system, you're adding water at times of the year when the rain-fed system is dry, so soil microbes in the irrigated system have ideal conditions to do their thing for more of the season than they do in the rain-fed system. So you lose more dry matter in the irrigated system than you do in the rain-fed system during that first year, and you also lose more for the buried cobs than you do for surface cobs. Turning to nutrients, the story is a little bit more complicated there, and it depends on the nutrient you're looking for. When you look at potassium isn't contained in any specific structures in the cob. It's not a part of a carbohydrate or a protein or anything like that. So when you get a rainfall event, either in late fall or a snow melt or something like that, the potassium in that residue is leached out of the residue very quickly. You use 80 to 90% of it from the residue. It's returned to the soil, and it could potentially be available to the crop. So that's a plant available nutrient that if you collected the cobs at harvest and moved them off site, you would lose. In contrast, nitrogen and phosphorus and sulfur are all part of proteins and carbohydrates and all kinds of other plant components, and they aren't leached out of the residue with those first rainfall events. And the amount of carbon relative to those nutrients in the cobs is very high. And microbes are just like us. We need all those things in the proper ratios to do their thing. So when they're breaking down their residue, they're using the carbon as an energy source, but they're retaining all the nitrogen and the phosphorus and the sulfur that they need to do their metabolic activity. So those nutrients are essentially retained within that residue for that first growing season. They're immobilized, they never become available. The carbon's respired and reduced, but the nutrient content in those cobs stays the same throughout that first growing season. So those fertilizer nutrients wouldn't be available to the growing crop the following year. Over the course of time, as that material is decomposed further, that carbon content will get low enough eventually that the nitrogen and phosphorus and sulfur and things will be mineralized and become part of the available pool in the soil.
You might be growing corn, you might be growing soy, sorghum, wheat, whatever you're growing crop-wise, but what you're really doing is you're farming your soil. You're farming your microorganisms because you want to maximize the soil organic matter that's in your soil because that is going to improve your soil fertility, and the activity of the microbes in that soil is going to help you increase the nitrogen release that's coming from that soil organic matter. So you're going to again increase the inherent soil fertility that you have. And this is what all of these management plans are going towards, is yes, we don't call this soil carbon, but it's the soil organic matter, how rich is your soil, that we're going back to as a metric of your soil health. So when Marty was talking about how greenhouse gases get factored into life cycle analyses to give us that apples to apples comparison between what's a fossil fuel based industry versus what would be an ethanol based industry, those calculations are taking into account not just CO2 or carbon dioxide, which is the main greenhouse gas that we consider, but also two other major ones, one being methane. There's not a whole lot of rice production around here that I've been able to see. I just got here a couple of years ago, but haven't seen much rice. Methane is mostly going to be coming from inundated cropping systems like rice, or perhaps sugarcane or something that requires a lot more water. If your farm is also associated with maybe livestock management, then methane would probably be something that would be counted into the account. The third major gas that we think of in those calculations for greenhouse gases is nitrous oxide. Nitrous oxide, it is the same stuff that your dentist gives you. It's laughing gas. It's the same stuff your dentist gives you if you go in there and you need to have a procedure done. And the nitrous oxide is pretty much a result of, again, biological activity in your soil that's related to your nitrogen management. So when we think about nitrous oxide production, nitrous oxide has some very specific soil conditions under which it's being produced. So we know that soil microbial activity is related to our soil fertility. Because what we can do is we can look at just one day, 24 hours worth of soil microbial activity in an ideally wetted soil, and we can relate that to the nitrogen mineralization rate out of that same soil. And we see this really strong relationship between microbial activity and nitrogen release coming out of that soil. Now this is pre-plant, pre-fertilization one-day CO2 out of the soil. If you use the same value right here, and you go to the end of the season, and you take a look at the nitrogen that's been taken up by your crop, that strong relationship continues to exist by the end of the season.